All right, silly people, here's the situation. Uh, this is just kind of a discussion about properties about the energies for um, wave functions in quantum mechanics. That is, that we're trying to show through some arguments that the value for the energy, E, uh, has to exceed the minimum value for the potential, um, V min. And to do that, the first thing we did is we rewrote the time-independent Schrodinger equation here in the form that Griffiths suggested. And it is quite suggestive because um, if E is less than V min, that is the minimum value of V of x, um, then this entire thing uh, is really weird. So if E is less than V min, then you actually have that d squared psi dx squared and also psi have to end up being the same sign. So in this case, d squared psi dx squared and psi have the same sign. Uh, what does that mean? To think about that, we're going to look at some like fundamental calculus stuff. So if you have a function and you take the derivative of that function and set it equal to 0, then uh, solve for x, then you find that x represents minimum or maximum for that function. And then the second derivative, when you set it equal to 0 and you solve for x, the sign of that value represents whether if it's a minimum or a maximum, pretty much. So just thinking about that. So if, let's look at the first case where if they're both positive. So if d squared psi dx squared, I don't know why I'm writing this in blue right now. Let's write it in black first. If d squared psi dx squared and psi are greater than 0, so they're both positive, then the wave function is going to be positive for all values of x. And also the second derivative of psi is positive, which means you can only have minimum values. So the wave function is going to look like this. Sheesh. It's going to have one minimum value and then shoot off. It can't have any maximums because it's always greater than 0, so it kind of just looks like that. And it has some minimum value here. It doesn't have to be at 0. I just drew it at 0 for illustration purposes. Then we kind of have a problem. This is for psi greater than 0. We have the problem that if we evaluate psi at minus infinity, or positive infinity for that matter, you get infinity. They both just kind of shoot off into infinity, which means it's impossible to normalize this. If a wave function was normalizable, then ideally those values would be 0. In this case, they're infinities, so we can't normalize them. Similarly, if we look at the case where the second derivative and the function are both less than 0, so they're both negative, then the wave function is negative for all values of x, and then the critical point represents a maximum. And there aren't any minimums anywhere in the function, so it'll look like this, and then shoot off to infinity again, where I guess the minimum's there, roughly. In this case, again, we find that if we let the wave function shoot off to infinity in either direction, now it's getting minus infinity, and that's equally unnormalizable for wave functions of this kind. So not looking good there either. And so ideally, a wave function which is normalizable will have the second derivative and the and the function at different signs. So let's set the second derivative to negative and the function to positive, which means that the wave function can only have maximums, and then the wave function is always positive, which means it'll look something like this. Or that one's a weird one. It'll look more like a Gaussian probably. So like wee, centered around some maximum that I kind of drew there on accident. But now you can see that the wave function has to converge to 0 whenever it shoots off to infinity. So now we have that psi minus infinity equals psi positive infinity equals 0. So we can normalize this actually, just doing the same process that we've been doing for a lot of the problems in this book so far. So yeah, energy is greater than V min. It's kind of fun, isn't it?